Hello everyone, and welcome back to Prep 3.4. So this problem is also going to be a two-sample z-test, as it says down here. And again, it's because we're going to be given the population standard deviation. So a regional sales manager at a nationwide electronics retailer wants to determine if there's a difference in the average number of units sold per day between two divisions, the East Division and the West Division. To investigate this, she randomly selects sales data from her database. The sample data shows daily units sold by sales associates from the East and West divisions. You can see here, East and West. Assume the population standard deviation for the East is 12 units and for the West is 15 units. At a significance level of 0.05, can the manager conclude that the mean number of units sold per day is higher for the West? Okay, so higher than is going to be one tail right. Distribution is Z because we have the population standard deviation. Sample size in both cases is given by count. So 40 in the East and 50 in the West. Okay, then we need the average, the East, and we need the average for the West. And then the expected variability. Okay, so that was given in the problem. For the East, it's 12. For the West, it's 15. So this is our first big important number, the observed difference between the two samples. So that's going to be equal to West minus East. So it's $2.75. So is that a big deal? Not a big deal? We're going to find out. So the null hypothesis is that there's no significant difference between the two populations, East and West, and the alternative is that the West is significantly higher than the East. Going back to our picture, the null hypothesis is here. They both belong effectively to the blue population. And if we reject the null, we're saying no. The West, which is the second one, the dashed line. See how we have a little dashed line here to match a dashed line here. The dashed line is part of a different population that's bigger. Okay, so let's calculate some things. What's our expected difference? Well, if they come from the same population, then when we subtract them, it should be 0. But we know there's going to be some variability, so let's calculate that. That's square root sigma squared divided by n plus this sigma squared divided by this n. Okay, so expected variability is 2.85. This is kind of interesting, right? The difference that we saw was 2.75. Expected variability is 2.85. Those actually look pretty close. If we look here, we can already get an idea of what's going on. So the observed difference was 2.75. Where that fits is it does seem to be in sort of the flow. It's about one standard error away, because the standard error is 2.85. So that does not look like a reject. We're not out here in the tail. We're sort of in the thick of things. But let's keep going just to make sure. So the alpha is 5%. Then we need all the critical values. The reason we do the two-tailed and the one-tailed right is because we need the two-tailed later on for the confidence interval for the population, even though we're actually going to use the one-tailed right for this problem. So equals norm dot S dot inverse, the probability divided by 2 because 2 tail, and then equals 1, equals norm dot S dot inverse 1 minus the probability divided by 2. And then this one's going to be really close to that because it's the right again. 1 minus, but this time 1 minus the whole probability, not divided, because it's all going to be in the right tail. Okay, then let's get our z-score, and the z-score is observed difference, which we know from above is the 2.75 divided by the standard error, which is 2.85, see, really close. So 0.96, and the probability of seeing a z-score of 0.96 is given by norm dot S dot dist z true. And the problem with this is that this is going to give us the probability on the wrong side, so we have to take the whole thing and subtract it from 1, and that gives us the probability on the right side. And you can see all of this over here. So there's the z critical, there's the 1.64, right, corresponding to 5% alpha. Here's our observation out here. The observed difference was 2.75, we saw that here. The probability is 16.74%, z-score 0.96. So we are clearly not in the rejection region, so we are going to fail to reject. In other words, what we're effectively saying is, look, it's very possible that both of these samples came from the same population. So, and we're making an even stronger statement. We're saying, don't make a business decision that West is bigger than East based on this sample, because that just might have been sampling error. So this is actually a pretty strong statement when we fail to reject. So fail to reject, and the reason is that probability, they probably come from the same population, and the interpretation is there's no significant difference. So we're not rejecting the null. All right, so now we could be falling into a type 2 error, which is that we're failing to reject the null hypothesis when it's actually false. In other words, what if there really was a difference and we just didn't pick it up? But, you know, there's always a possibility you're going to make a mistake. You do the best you can based on the accepted statistical parameters. All right, let's get the confidence interval. So let's first bring this back down, the observed difference. And then we subtract from that, take that observed difference, and subtract the two-tail times the standard error. And then we take the same number and add the two-tail times the standard error. And if we look at this in pictures, what we're effectively saying is that the true population is between negative, the true difference between these two is somewhere from negative, between the populations is between negative 2.83 and 8.32. And now you can see why it would be really dangerous to make a conclusion that West was bigger, because actually, with a different sample, it might actually even end up being smaller. So we're making no conclusion that they're different, which means, going back to the very original picture, we're saying they both belong to the blue population. And that's it for this one. We'll see you in the next one.